Okay, this is EPS version 2 hardware design review for OrcaSat. The point of this presentation is just to go over the schematics and the system design and just make sure that everything makes sense and there isn't anything weird going on and everyone's comfortable with what the EPS design looks like. So we'll start with the EPS architecture here. So on the left we've got solar panels. So these are the spacecraft's 5 solar panels. These are ORed or tied in parallel into a solar array through blocking diodes. And this solar array is then fed into the battery charge regulator right here. Battery charge regulator adjusts its output current based off of its input voltage. So it's a maximum power point tracking device. And this input voltage we can adjust. We can either leave it as a default value, which by default tracks to the voltage corresponding to a hot solar array. We can also feed in a signal, an analog signal from a DAC, which then adjusts, if you feed the signal in between 0 and 3 volts, it'll adjust the array voltage between a hot array and a cold array. And by doing that, we can then run maximum power point tracking algorithms elsewhere. But it's battery charge regulator, so it limits its output current based off of its input voltage, and it limits its output current based off of output voltage as well. But the primary control loop is the input voltage. We have a battery pack, which is here. We've got the low side inhibit and the 2 high side inhibits as per nanoracks requirements. The low side inhibits are actuated by this deploy 1 signal, and the high side inhibits are actuated by this deploy 2 signal. And both of those inhibits are actuated by the power control unit. So the power control unit contains the physical mechanical deployment switches, as well as the 30-minute timer, the heartbeat, reset logic, all of that fun stuff. So these inhibits here, these are just MOSFET switches, MOSFET power switches. These are not actuated directly by mechanical deployment switches. So the battery pack is not connected until the 30-minute timer has expired. It's a key thing to note there. Other designs connect the battery pack instantly upon exiting the deployer. This design basically remains disabled for the full 30 minutes. And then lastly, we've got the power conditioning distribution, which as far as most people are concerned, that is what the EPS is. So this includes all of the voltage conversion to generate the tightly regulated voltage supplies and all of the output protection and voltage and current and temperature monitoring that happens here. We'll have a look at what the actual hardware looks like. So this is the hardware connection diagram. So inside the spacecraft, right in the center here, you have the EPS module. It contains 3 circuit boards, the power management module, the power conditioning and distribution module, and the battery pack. So the power management module you can consider like the brains of the EPS. This contains the power control unit, which, as we talked about here, the power control unit is what controls the inhibits. It also contains the power monitoring unit, which is basically the telemetry collection component of the EPS. So I might refer to the power monitoring unit as the PMU or the TLM. TLM just means telemetry. So when I'm saying that the EPS TLM circuitry, I'm referring to power monitoring unit here. This is connected to a main board. So the power management module is a daughter card, and the main board here is the power conditioning and distribution module. So this contains all of the EPS power stuff. So it contains the battery charge regulator, contains the high side and low side inhibits, contains a 3-point, a 5-volt, and a 12-volt voltage converter, contains all the distribution E-fuses or power switches. It contains current sensors, temperature sensors, and voltage monitoring. And then there's this another connector, the battery pack connector right here. And then we have a battery pack which plugs into this. And the battery pack contains the batteries, and it also contains another PCB, which is a battery management system, which includes battery protection and some battery monitoring circuitry. This module sits inside the spacecraft, and we've got a bunch of connections to other things. So we've got deployment switch connectors. So these plug in, these are two harnesses that allow mechanical deployment switches to be inserted into the EPS module. So these are the mechanical deployment switches that sit in the rail ends, or they sit on the sit in the rails, and these are the switches that are actuated once the spacecraft is removed from the deployer, or they're actuated once it's put into the deployer, and then they're not. They are released once the spacecraft is ejected from the deployer. So you can plug deployment switches into it, and then you've got two solar panel connectors as well to plug in the solar array. So the RAM solar array contains the RAM, the starboard, and the port. So the port and the starboard connect directly to the RAM, and then you're running one harness from the RAM into the EPS. And we're using that same scheme on the other side of the spacecraft. The nadir and the zenith panels connect directly into wake, and then the wake connector, the wake harness, runs into the EPS. We've also got an external battery charger connection as well, so you can charge the battery once it's been integrated into the EPS and the EPS has been integrated into the spacecraft. We've also got a micro USB connector, which allows an external computer to be plugged in, and then that basically connects directly to the power monitoring unit, so you can pull telemetry off of the EPS. And there's a couple different configurations that you can do there, depending on if the EPS is fully turned on or if the spacecraft is fully turned on. And then lastly, you've got the main PC104 connector, which is the large primary interconnect. And this contains all of the signals to all other subsystems. So all of the voltage supplies, all of the enables and fault signals, and the SPI interface, and everything is connected over here. I will bring up one more block diagram really quickly, because I'll keep coming back to this. So this is the telemetry collection scheme of the power monitoring unit. So the basic idea here is you've got 32 analog channels between 0 and 3 volts, and you can feed any analog signal in here between 0 and 3 volts. This is muxed into 4 channels. Each of the 4 channels is buffered, and it's fed into a 4-channel 16-bit ADC. This 4-channel 16-bit ADC is connected to a 32-bit microcontroller, a SAMD21 chip, via I2C, and the microcontroller basically just pulls the ADC for data. So the basic scheme is you've got 4 muxes, and you're basically setting each mux address to channel 1, and then you're sweeping through the 4 channels on the ADC. Then you're setting the mux address to channel 2, you're sweeping through all 4 channels of the ADC, etc. And you're doing this, once every, basically as fast as you can. You're collecting data, and then the microcontroller is running some math to generate the number, which then once the OBC asks for telemetry, it's then dumping the computed number. So it's doing stuff like averaging and collecting max and min values and standard error and all that stuff. This diagram is out of date. It also shows that it's monitoring the end fault signals. That is no longer the case. It's not monitoring the end fault signals. And the reason for that is because the end fault signals don't actually mean anything unless you're also monitoring the enable signals, which was a change that I removed a while back, and I forgot to remove the end fault signals when I was making this diagram. So it doesn't monitor the end fault signals anymore. It only monitors the telemetry generated by the sensors. And then, of course, it has the USB to the EGSE interface. And this 32-bit microcontroller, because it's sampling all of this data, it's also sampling data about the array. And so it's able to run a maximum PowerPoint tracking algorithm. And I don't have it included here, but this outputs a adjust MPPT signal between 0 and 3 volts, which changes the array voltage that the maximum PowerPoint tracker should be tracking. And that's all of the important block diagrams for now. Let's get into some schematics. So this is the battery schematic here. It's very simple. I'm not going to spend too much time on this. Your main components is you got your battery protection IC. So this does overvoltage, undervoltage, overcurrent, short circuit, etc. This basically just monitors the voltage across the battery as well as the voltage across a shunt resistor. And it controls these 2 back-to-back high-side NFET switches. The main thing to note here is that this is meant for lithium-ion cells. So it's got an internal overvoltage protection value of 4.475 volts. an undervoltage value of 2.6 volts. We're using LTO cells in a 2S2P configuration. Their nominal voltage is around 2.4 volts, with their maximum voltage being 2.8 volts. So as you can see, we obviously can't use these cells with this battery protector, but by doing them in a 2S2P configuration, we get a voltage which is actually higher than the thresholds built into this BQ2980. And then we can use a voltage divider here to divide down the voltage sensed on the BAT pin. So it's a little bit of a hack, but it kind of works. The only downside to this is that now that you've got this voltage divider, this is constantly drawing current. And so this will slowly discharge these batteries, but luckily the requirements we have for how long the battery has to remain charged is not very demanding. And so having a few microamps trickle through here constantly isn't the end of the world. We've got a separate shunt resistor here, which is a 50 milliohm shunt resistor. This is being monitored by a analog current shunt sense amplifier, an INA 190. This is the same current shunt sense amplifier that we are using everywhere in the EPS. The difference is the gain is a little bit different. So this is a 25 gain chip. Everywhere else we're using a 50 gain chip, but we're using the same scheme with a 50 milliohm and an INA 190. And so this diagram here, all of the analog signals that are being generated that are for current measurements, they're all coming from these chips here. The important thing to note with this is that this is a bidirectional chip. So we're feeding this VREF signal in, which is 2.408 volts. If the current between positive and negative, if the current is flowing from positive to negative, sense P to sense N, it'll generate a voltage drop across P to N, which is a positive voltage drop between the in plus and in minus terminals. And that's a positive current as seen by this device. And a positive current will generate a positive output voltage of 2.048 volts to 3 volts. And because current is flowing out of the battery through the negative terminal, it means the current is flowing in through the positive terminal, which means the battery is charging. So a voltage of 2.048 volts means there's no current in or out of the battery, and 3 volts means it's the maximum charge current, which is about 2.66 amps. If you go the other way, if you discharge the battery, there's now a negative voltage drop, and so the output voltage will drop from 2.048 volts down to 0 volts, and that corresponds to a 0 amp to 5.6 amps of discharge current. We've also got temperature monitoring here. This TMP235Q1 temperature monitor. Once again, it's an analog output device, and this is the same temperature sensor that we're using everywhere else in the EPS. We also just have a very high resistance 1 meg voltage divider, and all of these signals are present on this TSM battery pack connector. Open up the PCB really quick. Should have opened this before doing the presentation because it takes a second to open, but we'll open it now. I'm right in the middle of routing this board out, but so it's kind of ugly. We'll just go into 3D mode so you can get an idea for it. On the back side, we've got the battery pack, or the physical cells themselves. So that the LTO cells, they look like big capacitors. We have these really nifty through-hole terminals that we solder in, and these terminals allow the batteries themselves to not have to be soldered in. So you solder these terminals in, and these are press, and then the battery press fits into these terminals. So you don't have to solder the battery leads themselves, which is great because there's a lot of copper in here. And if you wanted to solder the batteries in, it would take a lot of heat and a big soldering iron to actually solder the batteries in, as well as if we have an issue with one of the batteries that we put into this battery pack, we can actually just pull the battery out. We don't have to desolder it. So it's very useful. Whoops. Let's not do that. If you look at the top side, we've got the mounting holes for the okay, this is ugly. We've got the mounting holes for the battery pack mechanical holder, and then over here we've got the protection circuit. We've got the current monitoring, and then we've got the high side switch all the way over here, and we've got temperature monitoring. So very simple circuit, nothing really to talk about there. I'm just doing the layout right now, but you can see most of this is just giant copper pores because this board, the protection circuit doesn't kick in until it hits 8 amps. So this board has to be able to comfortably handle 8 amps before the protection circuit kicks in. All right, so let's jump over to the PCDM. So what I just showed you guys was the battery management system, or the battery pack PCB as it's known. Now we're looking at the power conditioning distribution module, which is this unit here. So this is the top level block diagram. I will revisit this diagram because the top level schematic is laid out to try and mimic this as much as possible. So we've got our arrays on the right here. We've got our array schematic symbol here, and we've got this is our charger schematic symbol, and this is our array schematic symbol here. Then we've got our BCR. We've got our battery pack connector, battery pack. Got our low side switch. We've got high side switch A, high side switch B, A, B, and we've got our power conditioning distribution unit, Power control unit is located on the power management module, and that's accessed via this power management module connector here. So all of the power management, or all the power control signals, are through this connector, and then our loads and everything else is through the PC104 connector, which is known as the primary I/O or CON I/O connector. On the top schematic, a couple of things to note. The battery pack mounting holes are connected to PCB ground, while the PC104 mounting holes are not connected to PCB ground at all, except for one. That's the chassis mounting hole, which is connected to the spacecraft chassis. That's all the metal in the spacecraft. And this is connected through a little 2.54 millimeter header on the external face of the EPS. And this allows us to basically break that connection really easily and then stick a continuity meter between the EPS ground and the spacecraft chassis ground to make sure that there isn't any accidental shorts to the chassis. And then for flight, we can remake that connection, and then the chassis is grounded. We can also just solder a really big 0805 0 ohm resistor if we don't want to do that, to make a more direct DC connection. But the thing to note that this is a star point ground or a single point connection ground, but it's a DC ground. There's no AC grounding or anything happening here. So we'll start with the solar array connector, and I have a diagram here. So the general scheme for the solar array connections is so there's 3 large panels and there's 2 small panels. The large panels each have 4 solar cells, and the small panels each have 2 solar cells. The connection scheme is exactly the same. Because we're tying this all together as an array and we're using only one BCR, we need to make sure that the voltage of this array is all the same. So we can't have like a 4S string of cells tied to a 2S string of cells. So they all have to be the same voltage. And because the minimum voltage is dictated by these panels that have only 2 cells on them, we basically just copy that scheme all the way throughout. So the small panels are just a string of 2 series or 2S cells. The large panels are just 2 strings of 2S cells. And then we have the blocking diodes, and then they're tied all together in parallel on the EPS. And then the maximum power point tracker is tracking that. The blocking diodes are to make sure that if there's a failure or if the cells are shaded, the other cells aren't discharging and back powering those cells. So if we open up the solar array connector schematic, you can see that that's exactly what's happening here. So we've got these Molex Pico lock connectors. This is where the starboard port RAM, these are the solar array, the 2S strings are being generated here. And then the 2S strings are being present here, and they're tied all together in parallel through these blocking diodes. And that generates the V array signal. We've also got temperature sensors on all the solar panels for monitoring temperature on the external faces of the spacecraft. And this is very useful for doing thermal simulation verification in flight. And so we need to send a 3.3 volt signal to power those temperature sensors, and it's called 3v3 TLM. This 3v3 TLM signal is only present when the N EPS TLM signal is pulled high on the PC104 header. So that's something I'll talk about a little bit later, but the basic idea of it is that all of the EPS power telemetry circuitry is off until the OBC commands it to be on, and that's to A, save power, but also B, if there's any issues with the microcontroller or any of the sensors, it can be easily reset by the onboard computer. If the device starts spitting out garbage data, it can be reset without having to kill the entire EPS and completely reset the spacecraft. And so each solar panel has a TMON signal, which is TMON, and then the name of the panel is behind it. And then that's fed into this MON array harness. If we go back to the top diagram, you can see this MON array harness. This is just fed directly into the CON PMM harness, or the CON PMM, the PMM connector, sorry, this MON array harness, because that needs to be fed to the power monitoring unit, which is on the PMM. And it doesn't go anywhere else. Let's look at the external charger. So the external charger is just a very simple 2.54 millimeter header. So we had this giant super high current Molex, I think it was a NanoFit or MicroFit connector on here. This has been changed because we don't actually need that much charge current anymore. Long story, but we're just using a regular 2.54 millimeter header like all the other headers on here. We've got an ESD protection diode, and then we've got an E-fuse here. And this is the same E-fuse that we're using on all of the power conditioning and distribution circuitry. These are the output switches that we'll talk about a bit later. I won't talk too much about this right now. It's the same schematic that's used everywhere else. It's basically just a power switch that's got some fancy protection features. So it checks for overvoltage, undervoltage. In this case, we're not using the undervoltage feature, but we are using the overvoltage feature. It also checks for current through the device, and if the current's too high, it opens the circuit. And it's got a power good threshold, so it monitors the output voltage and then has a flag, which is based off if the voltage is within the range or not. As well as it's got like a controlled slew rate, and it's got a fault timer. It's got a bunch of fun stuff. So it's a very, very powerful chip. And this is what we're using for everywhere. And as well as each IC also needs to monitor the current through it for each channel. So that's what we're doing here. But on the external charger, we're not actually monitoring the current. This IMON circuitry on the charger is not populated because we don't really care about the charge current. We can monitor the current out of the battery charge regulator, which is essentially the same as the current into the external charger. So we don't need that circuitry. We're just monitoring the battery charge regulator current, which is the next schematic. So this is the battery charge regulator. I won't spend a ton of time on this, just because this circuit we've already built and tested and we know it works. And nothing has really changed, or a bunch of stuff has changed, but it's relatively minor changes. So the BCR is an LTC3119. This is a switch mode buck boost regulator. Once again, it's got two control loops. So it's got this input, it's got the output control loop, which all regulators have, which is monitoring the output voltage, and then it's adjusting its output voltage to maintain a set output voltage. It also has an input control loop right here, this voltage divider, which is called MPVC. And this input control loop adjusts the output voltage and output current based off of the input voltage. One thing you will note is there's a ton of capacitance on here because when you're doing maximum power point tracking, the solar panels are highly resistive. So slight changes in current result in slight changes in voltage, and big changes in current result in big changes in voltage. So in your maximum power point tracking, you need to have a lot of capacitance to prevent the panel from really oscillating and causing problems and causing issues with this device trying to find a stable power point. The output, there's also quite a bit of capacitance as well. More capacitance is usually better. As far as sensors, we've got a temperature sensor, and we've got the same INA 190 chip that we're using everywhere else. So nothing too crazy here. The one thing that we are doing a little bit different is we are adjusting this. So by default, if we just removed this trace, it would just track to a fixed voltage. And this fixed voltage is set to 4.2 volts or 4.3 volts or something like that, which corresponds to the hottest array temperature after the estimated blocking diode drop of about 0.3 volts. So it's the hottest possible array temperature minus 0.3 volts is what this is tracking to. And the reason why we're doing this is because if you track to any other voltage, if you track to a really cold panel, yes, it won't be as efficient. You won't get as much power as you could out of the cold panel. But if the panels are hot, and you're tracking to a cold panel, then you can brown the panel out, because as the panel heats up, the voltage at max power drops. As the panel cools, the voltage at max power increases. So if you're tracking, and actually I can bring this up really fast if we must. Solar panel IV curve. Bit of a tangent here, but I think it's an important thing to talk about. So this is the IV curve of a solar panel. So as you draw more current out of the device, the voltage slowly drops, and then once you go to the short circuit current, the voltage quickly collapses. And this voltage at max power is the maximum power point of the solar panel. So you can draw a certain amount of current out of it, and the voltage only drops a little bit. And if you draw any more current out of it, then the voltage collapses. So you want to hover right around this point, where if you're drawing less current, then you're not getting as much power as the panel can generate. But if you draw too much current, then you're not getting any power. So that's what maximum power point tracking is about. But this VMP point, this voltage will move back and forth. It'll drift up and down as the panel heats up and cools down. So you have to track over temperature as well. And the effects are quite extreme in space, where the panel temperature is changing between minus 25 and 50 or 60 degrees. So you do want to track this. And the way we're doing that is we're just adjusting this voltage here. So this set to the hottest array, and as I said, with the hot array, the voltage will be, say, down here. And when you've got a cold array, the voltage is like way over here. Actually, I have a slide on this in the CDR presentation. Here's a slide right here. It's a very small diagram, but you can kind of get the idea here. Here's another one. That's for sunlight. You don't want that. But you can see the voltage point moves left or right depending on if the solar panel. So this is the hottest array. This is the coldest array. So the solar panel moves left or right. If the solar panel heats up or cools down, the voltage point, this voltage point moves left or right. So if you set the VMP over here for a cold array, but then the array actually ends up being hot and it's over here, you've now just moved up the curve, and now you're tracking. Now you're trying to track a point back on the curve that browns the panel out. So you always want to track for a hot array if it's fixed voltage tracking. Obviously, you lose some efficiency if the array ends up being cold most of the time, but that's why we have this circuitry here. So this allows us to feed a signal in, which is 0 to 3 volt signal from a DAC. And then this basically feeds in an error signal into this maximum power point tracking circuitry, which then adjusts the voltage seen by the array. So if you feed in 3 volts, it corresponds to the hottest possible array. And then as you feed in 0 volts, 3 down to 0 volts, it starts to increase the array voltage up to not the coldest possible array, but a very cold array. So we can gain back some of that efficiency if the array temperature is changing and we're losing a bit of efficiency there. And we've tested this circuitry. The main thing to note is that all the circuitry is powered off of VCC BCR. And this VCC BCR signal is generated by the battery charge regulator itself. So as soon as a voltage is applied to V array, and this voltage can be either generated by the solar panels and the solar array, or it can be generated by an external charger that's been plugged into it. But as soon as the voltage applied here, this battery charge regulator powers on and outputs VCC BCR. And this VCC BCR powers all of this circuitry, which then sets the BCR maximum power point tracking threshold to the hottest possible array. And then it's just sitting here waiting for a DAC signal from the microcontroller to then adjust it to be a colder array if needed. It's also important to note that as soon as there is sunlight or an external charger on this guy's input, it'll also output the VBat voltage signal. That's a very important thing to note. So the battery is not connected until the 30-minute timer has expired. So if I go back to the top here. So the battery is not connected until the 30-minute timer has expired, because this low side inhibit needs to deploy one signal to remain active. But the VBat to ground voltage is present as soon as there is sunlight or a charger has been plugged into the BCR. Now, that VBat signal is not present on VBus, and then the power conditioning and distribution stuff all remains off because of the high side switches, and that VBat signal isn't able to charge the battery because the battery is disconnected via the low side switch. So it's just an important thing to note. The VBat signal is present the second this thing basically deploys out of the deployer, but the EPS is still off because all the inhibits are disabled. And we'll talk about that in the power control unit in the PMM. Besides the BCR, that's pretty much it. There's nothing super interesting on the EPS. We'll have a look at the battery pack connector because this is slightly interesting. So the battery pack connector has pack plus, pack minus, and it's got the IMON signals. The important thing to note here is that the IMON signals, there's two harnesses. There's the MON pack sys and then the MON pack. If we go back to top, if we go back to top here, you'll see MON pack sys goes to the PC104 header, and MON pack goes to the PMM header. If we open up the PC104 header, this MON pack sys harness has IMON pack sys and VMON pack sys, and these are present directly on the PC104 header. And this allows the OBC to essentially kill the power monitoring unit and all the telemetry collection stuff, but it still can get two critical signals, which is the voltage of the battery pack and the current into or out of the battery pack. And so if the OBC monitors these two signals, we can collect the critical data about the battery health, which allows us to still, execute some basic mission and housekeeping tasks, knowing what the battery health is, without needing to turn on the entire power monitoring unit and all of the EPS telemetry collection circuitry. The problem with that, though, is if we go back to this, if we are feeding these signals are powered by the same voltage, this 3v3 CDH, that the OBC is powered by. So the OBC is powered by 3v3 CDH, and all the circuitry and all of the battery pack circuitry is powered by 3v3 CDH. So this pin on the back plate, this pin on the connector, pin 3, it's called 3v3 VBat here, but it's 3v3 CDH once you plug it into the PCDM. So all of that circuitry is powered by 3v3 CDH, but it's being monitored by circuitry which is powered by the 3v3 TLM signal, which is not enabled unless NEPS TLM is enabled by the OBC. So this is a huge problem because all the unpowered stuff and the ESD protection diodes and all that stuff, I kind of explain it here, would basically sink a ton of current out of these signals, and it would cause problems. So what we're doing is we're buffering it. So these buffers are powered by 3v3 CDH, but these signals aren't present, they're high Z, until it's enabled by the 3v3 TLM signal. And then we're just breaking out the IMON pack sys signals to the PC104 header, and the rest of the signals are being fed to the PMM. So there's something a little bit different that we're doing there. We also have this pack sense connector, which is just monitoring sense P and sense N directly across the battery pack. This is accessed via the external face of the spacecraft during vibration testing, so we can monitor, we can do in-circuit over open circuit voltage measurements of the battery pack. So the battery pack's connected, it's got the low side inhibit, so you can't just measure VBat to ground. If you want to actually measure the battery pack voltage while the spacecraft is off, immediately after a vibration test, you need to have this connector present, which is what we're doing here, because that's part of the NanoRacks requirements, is you need to do an open circuit voltage test before you do vibe and after vibe and make sure the voltage of the battery pack doesn't change. So that's what that's what this connector is for doing that measurement while the battery pack is integrated into the spacecraft and the spacecraft is off. Okay, low side inhibit, I'll move a bit quicker. Everything else is pretty straightforward. Low side inhibit is just two back-to-back NFET switches. On the low side, pulled to the pack minus, pack negative terminal, not ground, so that these, if the battery pack is present, it doesn't discharge and turn these switches on. And then we've got a PFET high side switch to control the logic here of turning this switch on or off. And the pull down for the enable from enable to COM is present on the COM PMM header. That was just to clean the schematic up and routing up a little bit. So I just put a note here that there is a pull down. This is defined as, the enable is defined as low, but it's on different schematic. And we've tested this and built this, and there's no concerns with that. For the high side inhibits, we switched this a little bit. So we were using the E-fuses before for these high side inhibits. We switched to a little bit more of a robust device for the high side There we go. So these are no longer E-fuses. These are just really beefy load switches or power switches. So these can do 10 amps, and they've got a quick output discharge functionality. So I'll talk about that for 2 seconds. What that does is well, first off, when you turn the enable on, the VOut is a controlled slew rate. So VOut doesn't instantly go to VN, it slowly goes to VN, and that allows capacitor charge current and load current to slowly increase and not, have this giant spike, this giant load current transient. So that's nice to have, but it also has quick output discharge. So when the enable is disabled, if VOut isn't just connected from VN, or VOut isn't just disconnected from VN. So most load switches will just disconnect VOut from VN. But if you've got a ton of capacitance here, like you've got hundreds of microfarads and you've got a very light load, when you disconnect VN and VOut, the output capacitance is actually able to hold the load up for a long enough time. And if you're just quickly cycling this, if say it was only, enabled and it's disabled for 1 second, then it's re-enabled, it might not actually be enough to reset the circuitry powered off of this. Especially things like voltage regulators, where the voltage regulator itself only draws a few microamps of current. The load that it's powering might draw milliamps or amps, but the voltage converter itself will only draw a few microamps. So if there's no load present, say you've disabled the load the voltage regulator is powering, so it's drawing maybe a few microamps of shutdown current, but then you're still having issues with the voltage converter has an overvoltage condition or something like that, and you want to reset the voltage converter. If you just toggle the input voltage, if you just disconnect it really quickly, the input capacitance to the voltage converter will actually be enough to hold it up and never reset it. So what quick output discharge does is when this is disabled, there's actually an internal FET, an internal 224 ohm resistor in here. And actually there isn't a resistor, just the FET is modulated to mimic a 220 ohm internal resistor. But anyway, the internal FET connects between VOut and ground, and that provides a low resistance path from VOut to ground to then discharge all of that capacitance. And because it's a well-defined 220 ohm resistance, you can then do calculations to know how long it's going to take for all of that capacitance to discharge through VOut and ground, so you know how long this enable pin has to be reset for. It's a very useful feature. All right, and last but not least, let's look at the PCD, power conditioning distribution unit. So we've got 3 voltage converters, and we've got a whole bunch of power switches. So each voltage converter generates a tightly regulated voltage supply, and that tightly regulated voltage supply is then shared between all of the channels that need that voltage supply, but then each channel has its own E-fuse, which is controlled by these enable signals, which are grouped here and pulled down, and then those are present over the control PCD harness. And I keep doing that. The control PCD harness is routed directly over the PC104 header. And the control PCD harness includes the enable signals and the fault signals. So the enables physically enable what channels are on, and the fault signals let you know if there's an issue where once a channel has been enabled, if it then shut off without toggling the enable pin, aka the fault protection shut it off, then the end fault signals are inserted and the OBC knows that, okay, something isn't on when it's supposed to be on. And then of course each generates an IMON signal. Each voltage converter generates a VMON signal, each voltage converter generates a TMON signal, and the VMON signal is just the output of each voltage converter, and all those MON signals are over the MON PCD harness to the power monitoring unit. Anything else interesting to talk about here? I won't go into super duper detail because these are all very simple circuits. This is the boost converter. It can do 1 amp at 12 volts, which should be enough to power the ADC and the payload. This is the buck boost converter. We're using this converter everywhere. We're using it for the 3.3 volt converter and the 5 volt converter, and we're also using it on the power monitoring unit. We've used this since day one with this Orcasat EPS comm set. This is a rock solid buck boost converter. It's awesome. It's extremely low noise, ridiculously efficient. It's one of the only voltage converters that actually, out of the box, all of these simulations and graphs I show in the datasheet, this thing like exceeds them. It's very impressive, and it's a relatively simple converter. Nothing really to note about this, except for the fact that it's got a power save feature. We can configure the power save feature to be enabled or not. I think what we'll probably do is for the 3.3 volt converter, we will enable the power save because so the power save increases the noise slightly, but it makes sure that the efficiency is high all the way down to like sub milliamps of load current. So we'll probably enable the power save for all the 3v3, but we'll disable it for the 5 volt because we're running the 5 volt TTC, and we just want to make sure that this is as clean of a rail as possible. And the 12 volt is powered by a different chip, which is this boost regulator, so it doesn't have the power save. Or it does have power save, but it's built in internally, I believe. Yeah, and then the eFuses, once again, I don't really have anything more to add. I said I was going to talk about it later, but I really don't have anything more to add besides just this is the eFuse. All pretty straightforward stuff, nothing too crazy happening here. And that is the PCDM. We can have a quick look at the COM PMM header. So these are all the signals that we're sending up to the PMM. And this is the CON.io, which is the PC104 header, and these are all the signals that we're heading up. So if you're looking at the schematics later on, just make sure that all of my signals are in the right place and everyone is expecting them to be. Let's have a look at the PCB. So this PCB is quote-unquote fully routed. I need to add some more silkscreen stuff. I won't go into the PCB layout because it doesn't really matter right now, but that's what the PCB looks like in 3D mode. As you can see, it's relatively high density. A lot of stuff packed in there. The chips up here, these are all the power switches, eFuses for all the output channels. These are the regulators, so that's the 12 volt, that's the 3 volt, that's the 5 volt. This is the battery charge regulator and the input blocking diodes. This is the external charge eFuse circuit. These are the two high side switches. This is the low side switch. And this is the buffers for the battery pack, as well as the analog inputs, like the analog MPPT adjust signals and whatnot for the BCR. So it's all relatively simple. Some of the features to note is we've got these really nifty edge mount test points. We don't have to assemble any test points. You can just grab the little grabber hooks, and you can just grab these test points for common signals that you want to sense. As well as we've got the PMM connector here. We've got the battery pack connector, which sits on this side, but it's not populated right now. And we've got the PC104 header, which is there. We've got 3 connectors, which are external on the external face of the spacecraft. This is the chassis ground connection here. This is the battery pack sense connection here. And this is the external charge connection here. And on this side of the spacecraft, we've got the RAM and wake solar panel connectors. We've got the grounded mounting holes, and oh, look at that, found a mistake. I forgot to put keep outs on my mounting holes. Place a note. I wasn't done routing that board, but I need to add that right here. Put keep outs on mounting holes to prevent pores from pouring into screw head keep outs. I can't think right now, but you get the idea. I need to make sure that I do that. I wasn't done routing it. I need to add some silkscreen stuff, and I probably would have caught that, but always good to add a note just in case I'm going crazy and I don't catch it. All right, last but not least, and this is just what the layers look like. So the top layer is mostly components, as well as there is a top ground pour on here. I haven't looked at all these pores too much in detail. I kind of just finished this, then move on, but I will come back to this and revisit this. Then you've got layer 2, which is a full ground pour. Layer 3, which is a power pour for 3v3 TLM, as well as I've got a couple other pores on here doing little weird things, but it's just a 3v3 TLM pour, basically ground. And then we've got the bottom layer, which is all of the signal routing, as well as a few high current traces that need to exist down here. That's the board. It's pretty simple. A lot of components, but the routing is not too bad. All right, and let's wrap it up with the power management module, PMM. So on the PMM, we've got two connectors. We've got the PMM connector. This is all the signals to and from the PCDM, as well as the deployment switch connector, or deployment switch connectors, I should say, which connect the physical, mechanical deployment switches into the PMM. There's three main kind of circuits on the PMM. There's the power circuit, so this generates all the voltage rails needed for all the stuff to work. There's the power control unit, which generates the deploy 1, deploy 2 signals. It also requires the heartbeat signal. So once the deploy 1 and 2 signals go high, it needs this heartbeat signal to keep the EPS deployed. And this heartbeat signal is generated by the onboard computer. And then we've got the power monitoring unit, which just monitors all of the MON signals and then controls the maximum power point tracking via this MPPT harness. And it controls and it talks to the OBC via this SPI harness. So let's have a look at the power first. So the power circuitry takes this VBat signal and it regulates it to 3.3 volts, which is 3.3 volt PCU. So the important thing to remember here is, I mentioned this earlier, but I'll reiterate again, this VBat to ground voltage potential, this is generated as soon as the spacecraft is in sunlight. But the battery pack remains disconnected via the low side switch. So when the spacecraft is deployed, if it's deployed in the eclipse, we won't have this VBat voltage. If it is deployed then we have to wait until it comes into the sun. But as soon as the spacecraft is deployed and it's in the sun, this VBat voltage will be present even before the spacecraft deploys, because you need it to deploy the spacecraft. And you'll see, I've got this, whoops. Where is this? Here we go. So this sums up the power control unit pretty well. So let's have a look at this. So this here is VBat. I didn't put a label on it, but this is VBat. So VBat is connected to VIN on the buck boost converter. As soon as VIN is present, VOut is generated, except there is an enable pin here. And that's what these physical deployment switches and RBF switches are controlling, is they're controlling this enable pin. So if the RBF is inserted or the mechanical deployment switches are all open, which they're normally closed, so if the deployment switches are all actuated or depressed, or whatever you want to say, actuated I think is the correct term. If all those switches are actuated, or any pair of switches is actuated, such as the spacecraft is inside the deployer, or the RBF is inserted, then this enable signal is low, and it doesn't matter if you got a voltage on VN or not, there won't be a voltage on Vout. If the RBF is removed and the deployment switches are not actuated, meaning that they're the switches themselves, the levers aren't pressed on them, then these switches are normally closed, which connects VBat to N, enabling the buck boost converter. And so once the buck boost converter is enabled, assuming these switches are not actuated and the RBF is removed, as soon as there's a voltage present on VBat or VN, this 3.3 volt PCU, 3v3 PCU signal will be generated. And I said this again, but I'm going to hammer it home. VBat is present as soon as the spacecraft is in the sun. As soon as the spacecraft is in the sun, it doesn't matter if 30 minutes has gone by or not. All of this timer control circuitry, this is all powered by 3.3 volt PCU, right? To generate the deploy 1 to deploy 2 signals. Deploy 1 signal connects the low side inhibit, deploy 2 connects the high side inhibits. So those inhibits are disabled because all of this 3v3 PCU stuff is off. It's only once VBat is on and VBat turns on as soon as the spacecraft is in the sun. So kind of hammering this over and over again, but it is kind of a weird concept to think about, where because it's called VBat. I think that's what throws me off anyway. It's not actually the battery voltage. It's the maximum power point tracker BCR output voltage is what's on. The VBat doesn't have a voltage across it. If you're in the eclipse, it's not on because it has a low side inhibit, which is disabled. Anyway, once CV3 PCU turns on, it enables this 30-minute timer. It enables this watchdog and enables this 10-second timer. So all of this circuitry is powered by 3v3 PCU. After 10 seconds, these are all power on reset timers. So their outputs, once they receive power, their outputs remain low for the program time, and then they go high and they stay high indefinitely until they're reset. So reset via the end reset pin. So they stay high forever if once they expire, unless they are reset. I realized I said that kind of weird earlier. So the first timer to expire is the 10-second timer, and it drives its output high, but its output is fed into this AND gate. So it needs to wait for the 30-minute timer to also expire for this logic to be true. When the 30-minute timer expires, it directly enables deploy 1, which connects the battery pack to the spacecraft. So you do need to remain in sunlight for 30 minutes for deploy 1 to connect, thus connecting the battery pack, which then keeps the VBat signal present while the spacecraft is in the eclipse. The good news is that the minimum eclipse period is like 60 minutes or something like that, or 50 minutes or something like that. So there's more than enough time to run this. And also, this circuitry consumes essentially no current on the order of microamps. So it's not like, if the panels are damaged or whatever, there is enough power. Basically, as soon as there's any photons hitting the panels, this 30-minute timer can turn on. Once the 30-minute timer expires, the 10-second timer expired a long time ago. So both of those signals are high. The AND logic is true. The deploy 2 signal is also high. The deploy 2 signal is what connects the high side inhibits, which connect VBat, which is a combination now of the BCR and the battery pack voltage, because the low side inhibit is enabled, to VBus. And as soon as there's a voltage on VBus, all of the regulators turn on, and 3v3 CDH turns on by default. The enable is just pulled high. So as soon as it receives power, all of the stuff turns on. Every other channel remains disabled until the OBC commands it to via the N signals. But once deploy 2 goes high, deploy 2 enables a watchdog timer. So the watchdog timer, once it's enabled, it waits for about 2.5 seconds, and then it starts wanting a heartbeat signal on its watchdog input. The watchdog input is given by the OBC, and we're looking at a 1 hertz heartbeat signal. So 2.5 seconds after deploy 2 is enabled, the voltage, the 3.3 volt, the high side inhibits turn on, which happen in milliseconds. The 3.3 volt voltage converter, I'll go back to the schematic so people can see what I'm talking about. So once deploy 2 turns on, the 2 high side switches enable in milliseconds, which then provides VBus. Once VBus is enabled, the 3.3 volt converter enables in milliseconds as well, 100 milliseconds or something like that, for 3.3 volts to be enabled. And once 3.3 volts is enabled, 3v3 PCD is enabled, then the 3v3 CDH is enabled like 1 or 2 milliseconds after that. So on the order of milliseconds, you've got 3v3 CDH. So from the time deploy 2 goes high till the time 3v3 CDH goes high is milliseconds. And this heartbeat signal, this watchdog, once it's enabled via deploy 2, so deploy 2 goes high, and then milliseconds later, 3v3 CDH goes high, and the OBC can power on. And then seconds later, 2.5 seconds later, it wants a heartbeat signal. So it's more than enough time for the OBC to power on, but it is something we will be rigorously testing to make sure there is no condition present where the OBC goes into a weird boot mode and it can't pet the heartbeat. But once deploy 2 goes high, enables the watchdog, and it waits for a heartbeat. If the OBC is booted successfully and everything's happy, the heartbeat signal is being provided, and the watchdog input remains low, and the reset is not present. If the heartbeat signal dies for any reason, 2.5 seconds after it dies, the watchdog timer expires, and it asserts the watchdog output, which resets the 10-second timer. As soon as the 10-second timer is reset, its output goes from high to low, and as soon as it goes low, this AND logic is broken, which means that the deploy 2 signal is now gone. The deploy 2 signal goes away. Deploy 2 signal goes away means the watchdog is now reset. So if the watchdog is reset, then its watchdog output also is no longer asserted, which then allows the 10-second timer to start up again. But the reason why this doesn't oscillate and go all crazy is because the 10-second timer is a power on reset timer. So as soon as it's no longer reset, its output still stays low for 10 seconds until it goes high, and then the cycle repeats itself. And we've tested this. This has been more or less the design for the proof of concept and EPS v1, and this works fine. So back to the power here. So that's what I was talking about, where I was saying 3v3 PCU is present as soon as VBat is present. If actually I should that's what I should look at first, is the deployment switch connectors. Sorry. So deployment switch connectors just connect VBat to NPCU, as we talked about earlier. This is the deployment switch configuration. We've got a wetter circuit in here, which is a 1K and a 220 microfarad capacitor. This allows a quote-unquote large current, it's just milliamps, to be present as soon as your switches are connected. This burns off oxide on the switches, also known as switch wetting. It's a relatively important thing to have on micro switches when you're not switching a ton of current. We also have this RBF pin, which is just a 3.5 millimeter audio jack, some ESD diodes, because if we decide to machine a metal RBF pin, it actually will conduct, and it will be a very good place for ESD to enter the spacecraft. And the RBF pin has its own wetter circuit as well. And then NPCU is pulled down through a 1 mega ohm resistor here. So that's the circuit there. So if we go back to power, once again, if NPCU is high and VBat is present, 3v3 PCU starts and the deployment of the spacecraft starts. Also in the circuitry, we have the 3v3 TLM voltage, and this is just generated off of 3v3 PCU, but there's an E-fuse here, and this E-fuse is controlled by this NEPS TLM signal. So 3v3 TLM just stays off. It's pulled down to low. This chip is never enabled unless the OBC forces the NEPS TLM signal high, and this NEPS TLM signal is present over the PC104 header. And there's a corresponding fault signal for it as well. And we've got temperature monitoring, current monitoring, the usual. Let's have a look at the power control unit. Almost exactly the same as the block diagram, but we're using a 3-input AND gate instead of a 2-input AND gate. And the reason for that is because I wanted to add this reset deploy 2 jumper, which basically, no matter what happens, if this deploy 2 jumper is inserted, reset deploy 2 jumper is inserted, deploy 2 is never asserted. And this was the easiest way of doing it, was switching to 3-input AND gate. But this jumper is very useful for charging the battery. So if you charge the battery, you're plugging an external charger in, which enables VBat. And as soon as you enable VBat, if your RBF pin is not connected and the deployment switches aren't actuated, then not only will the battery begin to charge, well, the battery won't begin to charge immediately, but in order to charge the battery, you have to enable the lowest side inhibit, which means all this power control unit turns on because 3v3 PCU is now present. Spacecraft deploys, but guess what? If spacecraft deploys, it also enables deploy 2, which, enables all the rest of the signal chain stuff, including the heartbeat. So sometimes you just want to enable deploy 1, because deploy 1 is the low side inhibit, to charge the battery. And so that's what this reset deploy 2 jumper does. It just kills the high side inhibits and never allows them to enable, which also never turns on the watchdog, and it never turns on the OBC or anything else. And this is just so if you want to just charge the battery on the spacecraft and do nothing else. But this is the 30-minute timer, programmable oscillator configured as a one-shot timer. This 10-second timer is the same chip, just programmed as a one-shot, programmed slightly differently. And this is the watchdog timer. It's exactly the same as the block diagram I presented. There is a couple jumpers on here to do different things. The fast deploy jumper just ties in another resistor in parallel, and it sets the time from 30 minutes to about 1.5 seconds. This allows us to not change anything in the schematic, but makes testing a hell of a lot easier, so we don't have to wait 30 minutes to see if the deploy 1 signal comes up or whatever. We can just short this timer, and 1.5 seconds later the EPS is deploying. We also have this reset heartbeat jumper, which is very useful for if we want to do a full deployment of the spacecraft. We want, we want the 3.3 volt CDH signal to be present and whatnot, but we don't want the heartbeat feature to be, we can then just insert this header. And this is mostly for EPS testing itself because, you know, I want to enable all the output channels and make sure stuff is working properly, and do a bunch of testing on the output channels with the PMM integrated on here. But I don't want to have an Arduino generating a heartbeat signal to keep the EPS alive. So this is mostly what this jumper is here for. All right, and last but not least, let's look at the PMU. I'm at 1 hour now, so I'll try and go a little bit faster here. So PMU, not a whole ton to talk about here. AT-SAMD21. Yeah, it's the same chip as the Arduino Maker Zero. We're copying the pinout for the, I believe it's the Metro M0 Express from Adafruit. We got a USB connector here. We've got an I2C connector, so we can just plug I2C devices in and play around with firmware, or directly access the ADC I2C interface over this header. We've got our SWSCLK and SWDIO for programming, as well as this reset header here for resetting the EPS during programming, and also just resetting the EPS by itself. We've also got this nice little header here which breaks out a bunch of the unused signals on the microcontroller for just general firmware development, prototyping, etc. A couple of analog, a couple of digital pins on there for the Arduino. And then we've got all of our muxes. So these are 32 analog channels muxed in into 4 analog channels, which are fed into the 4 analog channels on the ADC. We have also got a watchdog. This is the same watchdog as the watchdog used for the heartbeat timer, for a watchdog on the microcontroller. I'm actually not totally sure if we're going to use this. This circuit works exactly the same in terms of keeping the reset pulled high and then having a jumper to reset the microcontroller, regardless of if this circuit's populated or not. So I've included it here, but I don't think we really need it because the microcontroller is powered by a 3v3 TLM, which is enabled by the N EPS TLM signal. So if there's any issues with microcontroller, you know, the OBC can just have like a simple timeout type thing where if, you know, the EPS doesn't respond in 2 or 3 seconds, it just resets N EPS TLM and then re-enables it, or we can do it manually from the ground. So I don't really know if a watchdog timer is super important here. Yeah, I've included it. That's one of those things that we'll just have to test with and just see if it actually is a useful thing. And there's a 16-bit ADC. We've got a couple LEDs. These won't be populated for flight. They're just here to help make debugging and testing easier. Then all of our mon signals come in. All of the voltages are divided down to be between 0 and 3 volts here. And if we have a look at the muxes, it's a analog mux, TMUX 1308, but this follows the same footprint and the same standard as all the other analog muxes on the market. And then we were just buffering this here to A out. And that's pretty much it. There isn't anything else to talk about. Take a quick look at the PCB, I guess. I think I've covered everything. Much better to have a presentation, but it only takes me an hour to do these videos. It takes a lot longer to make a presentation. So this is the board without any of the pores on it. If we go into 3D mode, so this is the external face here. So we've got the fast deploy jumper, we've got reset deploy 2 jumper, and NEPS TLM jumper. So these are the 3 critical jumpers for the EPS. So the fast deploy jumper allows you to like turn the spacecraft on without having to wait 30 minutes. Excellent for testing once the spacecraft is fully integrated. Reset deploy 2 jumper, this, no matter what you do with the EPS, this prevents the OBC or any other load on the spacecraft, or any of the power conditioning and distribution circuitry from powering on. So this is mostly used for charging the battery. So you can plug the battery charger into it, and you don't have to worry about the OBC or any of the loads powering on. And you got this N EPS TLM jumper. This jumps the N EPS TLM signal high, and because the NEPS, or not NEPS, because the 3v3 TLM, all of the power monitoring unit is powered off of 3v3 TLM, and 3v3 TLM is derived from the 3v3 PCU signal. This allows you to do stuff like if you're charging the battery, then that 3v3 PCU signal is present. So you can also then jump NEPS TLM, and now the microcontroller will turn on and you can actually access it via this USB connector here. So you can charge the battery, you can pull TLM directly off the microcontroller while you're charging the battery, but none of this loads on the spacecraft are on. assuming these two jumpers are plugged in. And of course, you got a whole bunch of different modes of operation depending on which configuration these jumpers are put into. You can fully deploy the spacecraft and have the OBC boot, but still pull data off of the microcontroller, etc. This is the remove before flight pin here. Just this big 3.5mm audio jack. If we go back to the top of the board here, along the sides we've got the non-essential connectors that are really just here for testing. So we've got the debug, reset, I2C, a couple of ground pins for just general things. We've also got a heartbeat pin here, so you can just feed a heartbeat in via an Arduino or whatever. You don't need to use the PMM connector. This is a deployment switch connector here. We've got another complementary pair of deployment switch connectors on the other side. We got the reset heartbeat jumper and the NPCU jumper. Yeah, and then this is the Arduino like breakout pins for the unused pins on the microcontroller. Watchdog microcontroller and its crystal. These are all the muxes and buffers. This is the 3v3 PCU regulator. This is the 3v3 TLM eFuse. Temperature sensor. This is the 16-bit ADC. And then this is the power control unit stuff. So 1-timer, 2-timer, AND gate, and then the watchdog timer here. If you look at the schematics, all pretty straightforward, just easy routing. Tools, polygon pores. So top layer, just some basic routing and a few ground pores here. Solid ground pour. All 3v3 TLM. Ground pour. Actually, just realized I misspoke. Layer 3, I believe, is ground. No, layer 3 TLM. Never mind. Sorry. There's a 3v3 PCU pour here, and then all the rest is 3v3 TLM. And then bottom layer is just more routing. Pretty easy boards to route. The PCU is very simple board. There isn't a whole lot on it. And that's the video. I think I covered everything that's important. I hope that my narration provides useful insight to people that are looking at the Altium schematics and wondering why things are the way they are. I will be kind of redoing this presentation in a physical presentation form with nice slides that go into more detail about all the design decisions and whatnot. But that takes a lot of work to do because the documentation doesn't exist, and more block diagrams and presentations I have to make. So I will be preparing those as the final documentation for the EPS, but for now, before we manufacture the EPS, this will have to do. So thanks for watching, and yeah, any questions, let me know.